Let knowledge flow like a river, without any hindrance. Don't make it like a stagnant pool. Hello everyone. I'm PS Chaturji, and welcome to my channel. Today's video is titled Excel for IS456 Beam Design, Bending, with SP16, Part 2. I hope you've already watched the first part, Excel for IS456, Single Reinforced Section and Steel Percentage with SP16 Part 1. If not, please do watch Part 1 to get a good grasp of this video. In this video, we'll use the Excel formulas demonstrated in Part 1 for the analysis of a singly reinforced concrete section. This is the first in a series of DIY projects for civil engineering. In this DIY project, I'll cover Excel operations such as drop-down menus, defined names, and conditional formatting. I've created previous videos on these topics, and I'll include the links in the description for your reference. A tip for my non-civil engineer viewers: if you are not a civil engineer, don't worry about the terminology. Simply treat each operator as a number and apply the procedure to your own projects. Many viewers have directly emailed me requesting the free Excel sheet. To receive it, please send an email with your request and leave a comment on the relevant video stating that you've sent an email. This is required. After receiving the file, please acknowledge receipt in the comments section of the video. This process helps me and other viewers, and also allows me to validate and deepen my own understanding through the free sharing of this knowledge. I appreciate your cooperation. From start to finish, I've enjoyed the assistance of Gemini AI, free of charge. Thanks to Gemini AI for its active support. If you find this video useful, please like, share, comment, and subscribe. Let's begin our new journey. Now, we're on the dashboard, ready to demonstrate my first DIY project on single reinforced beam section design. I've highlighted the primary input data required for the design and calculation of a single reinforced section with a white box. As you can see, this includes grade of concrete, grade of steel, clear cover, modulus of elasticity for steel, width of the beam, overall depth, ultimate factored moment, MU, ultimate factored shear force, VU, main bars combination, minimum percentage of steel required, and shear bars. Below this, there's a green box labeled formulas. I'll create a drop-down box here for demonstration purposes, to clearly show you the actual formulas and methods used. In practice, this box isn't required. First, I'll create this formulas box. I've listed all the necessary formulas on sheet 2. To do this, first, click on the Home tab, then go to the Data tab on the ribbon. Next, click on Data Validation, and then click on Data Validation again. Select the List option. Then, click on the Source box, go to Sheet 2, and select cells A1 to A15. Click OK to accept data. Our first drop-down menu is now ready. In this video, I'll cover beam design for bending stress only. Next week, I'll provide a tutorial on the design for shear stress. Now, let's set up the data input for concrete grade. To do that, I am selecting option 1 in the formula box. On the formula box, you'll find the possible concrete grades as per IS456, ranging from M10 to M100. These are further divided into three categories: M10 to M20, ordinary concrete; M25 to M55, standard concrete; and M60 to M100, high-strength concrete. First, I'll copy the concrete grades. Then, I'll go to the Data tab on the ribbon, click on Data Validation, select Data Validation again, and choose the List option. In the source box, I'll paste the data copied from Sheet 2. Click OK to accept data. Now, our second drop-down menu for selecting the concrete grade is ready. I'll select M10 from the drop-down. Next, I'll format this cell for a professional look. I'll select the cell, right-click, choose Format Cells, go to the Number tab, select Custom, and type M within quotation marks, followed by a single-digit 0. Our cell formatting is now ready. Now the cell displays M10, where M symbolizes the concrete grade. Now, I'll apply conditional formatting. I'll select cell A4, go to the Home tab, choose Conditional Formatting, and select New Rule. I'll select the Format Only cells that contain rule, set the cell value to less than or equal to 20, and format the fill color to yellow. Click OK to accept the condition. Our conditional formatting is now ready. As per IS 456, M10 to M20 grades are designated as ordinary concrete, which is not recommended for important structural elements. Therefore, when we select a grade from M10 to M20, the cell will be highlighted in yellow as a reminder. Since we've selected M10, the cell is yellow. Now, I'll fill the cell by green color and select M25. The cell turns green, indicating that our selection is acceptable. Save the file. Alright, let's now focus on setting up the input for the steel grade. On Formula box, I am selecting option 2, you'll find the available steel grades as per IS 456, ranging from FE 250 up to FE 600. These are broadly categorized into FE 250, which is mild steel, and FE 415 to FE 600, representing high-strength deformed bars. To begin, I'll copy the list of steel grades. Next, navigate to the Data tab on the Excel ribbon. Here, we'll click on Data Validation, and from the drop-down, select Data Validation again. In the Allow field, choose the List option. Now, in the source box, simply paste the steel grades we just copied from Formula box. Click OK to confirm. And just like that, our drop-down menu for selecting the steel grade is now ready. Let's select FE 250 from this new drop-down. To enhance the visual presentation, we'll format this cell. Select the cell, right-click, and choose Format Cells. Go to the Number tab, select Custom, and in the Type field, enter FE enclosed in quotation marks, followed by a single 0. Click OK. You'll now see the cell displays FE 250, where FE clearly indicates the steel grade. Now, let's implement some conditional formatting. Select cell B4, go to the Home tab, and click on Conditional Formatting. Choose New Rule. Select the rule type Format Only cells that contain. In the drop-down, ensure cell value is selected, and then choose Equal to and enter 250. Next, click on the Format button, go to the Fill tab, and select a yellow color. Click OK on both dialog boxes to apply the rule. Our conditional formatting is now set. According to IS 456, Fe250 is classified as mild steel, which is generally not preferred for significant structural applications. Therefore, as a visual cue, when Fe250 is selected, the cell will automatically highlight in yellow. As you can see, with Fe250 selected, the cell is indeed yellow. Now, I'll fill the cell by green color and let's change the selection to Fe415. Notice how the cell color changes to green, visually confirming that this is a more commonly accepted grade. Save your work. Alright, let's now define the essential properties of our beam. We'll begin by setting the clear cover to 25 mm. Following that, the width of the beam will be 250 mm, and the overall depth is 450 mm. Next, we'll specify the reinforcement in the tension zone as 3 numbers of 20 mm diameter bars, in the layer 1. Now, let's input the ultimate factored moment, which is 50 kN/m. You might notice the units appearing automatically after each entry. This is due to pre-applied cell formatting. To keep things efficient, I won't be demonstrating that formatting process in detail here. However, the underlying method is similar to what we did earlier, with the key difference being the positioning of the unit on the right-hand side of the single-digit 0 format. Finally, we'll also note the minimum percentage of steel required, which is 0.2%. Remember to save your work. In this part of the video, we're going to learn about using an Excel feature called Define Name. This allows us to give unique, descriptive names to individual cells or ranges. Before we jump in, let's understand why giving unique names using the Define Name option is so useful. Here are the key reasons. 1. It lets us treat cell references as absolute or fixed. This means that when we use these named cells in formulas, the reference won't change even if we copy or move the formula. 2. In this project, we'll be working with several formulas. Giving each important input cell a unique name makes it much easier to identify and understand what each part of our calculations refers to. It brings clarity to our formulas. 3. Think of it like preparing your workspace before starting a big task. It's like clearing away any clutter so you can work more efficiently and avoid confusion later on. 4. Once we've finished setting up our calculations, if we need to move the position of any of our input cells for better organization, using defined names ensures that our formulas will still work correctly and our results won't be affected. 5. Making formulas easier to read and understand, reducing the risk of errors in formulas, and simplifying navigation within the spreadsheet. For example, let me show you how to apply Define Name to cell A4, which we're using for selecting the grade of concrete. You can then follow the same steps for the other cells yourself. First, select cell A4. Next, go to the Formulas tab on the Excel ribbon. Within the Defined Names group, click on Define Name. You might notice that Excel automatically suggests the name FCK based on the text in the heading. While this suggestion can be helpful, you can always choose a different name if you prefer. Since FCK is a commonly understood technical term for concrete grade among civil engineers, I'm going to accept this suggested name. Click OK. Now, instead of referring to cell A4, we can use the name FCK. You'll need to follow this same process to give a unique and meaningful name to each of the important input cells in your spreadsheet. Now, I am removing the cover from the bottom portion, and I will input the formulas one by one for the design calculation of the beam. From the drop-down menu for formulas, I am selecting the formula for effective cover. The name of this cell is D_EFF. D_EFF equals to D minus CO minus dia_01 divided by 2. Where D equals overall depth, CO equals clear cover, and dia_01 equals the diameter of the bar at the bottommost layer. By copying this formula from the formula box, I am pasting it into cell A13, and you are watching the value of effective depth equals 415 millimeters. Next, I am selecting the formula for XU max by D from the drop-down menu, and we are watching the formula for XU max by D is equal to 0.0035 multiplied by ES, divided by 0.0055 plus 0.87 multiplied by FY divided by ES. Here, XU max by D is the ratio of the maximum distance of the neutral axis and effective depth of the beam from the top of the beam. ES is the modulus of elasticity. The value of ES equals 200,000. Fy is the grade of steel. The selected grade of steel is 415. By copying this formula from the formula box, I am pasting the formula into cell B13. The value of XU_max_D equals 0.479, and the name of the cell is XU_max_D. Since it is the ratio of two lengths, XU_max_D does not have any unit. Next, I am selecting the formula for the percentage of steel provided, PT_PROV. The formula is equal to 100 multiplied by NO_01, multiplied by 0.25, multiplied by pi, multiplied by dia_01 to the power 2, plus NO_02, multiplied by 0.25, multiplied by pi, multiplied by dia_02 to the power 2, divided by B multiplied by D_EFF. By copying this formula, I am pasting it into cell H13 and we are watching the value of PT_PROV equals to 0.908%. Here, NO_1 and NO_2 are the number of bars for layer 1 and 2 respectively, and dia_01 and dia_02 are the diameters in millimeters of the bars respectively. Next, I am selecting the formula for XU by D from the drop-down menu. Now we are watching the formula for XU by D is equal to PT_PROV divided by 100 multiplied by 0.87 multiplied by Fy divided by 0.36 multiplied by FCK. Here, XU by D is the ratio of the calculated distance of neutral axis and effective depth of the beam from top of the beam. PT_PROV is the percentage of steel provided. FCK is the characteristic strength of the concrete. here it is 25 Newton per square millimeter. By copying this formula from the formula box, I am pasting the formula into cell C13. We are watching the value of XU_D equals 0.364, and I have provided the name of the cell as XU_D. Once again, it is the ratio of two lengths, and XU_D does not have any unit. Next, I am selecting the formula for mu lim by BD squared. This is equal to round 0.36 multiplied by FCK multiplied by XU_max_D multiplied by 1 minus 0.416 multiplied by XU_max_D, up to 3 digits. By copying this formula from the formula box, I am pasting the formula into cell D13, and the name of the cell is mu_lim_b_d_2. Here, D equals D_EFF, and the value of mu_lim_b_d_2 equals 3.453 Newton per millimeter squared. mu_lim_b_d_2 is the limiting or maximum bending stress that we can consider for our design. Next, I am selecting the formula for mu by bd squared. This is equal to mu multiplied by 10 to the power of 6, divided by b multiplied by d_EFF to the power of 2. By copying this formula from the formula box, I am pasting the formula into cell E13. Now we are watching the value of mu by bd squared equals 1.161. Here, mu is our calculated factored moment. Since the unit of mu is kilonewton meter, we multiply it by 10 to the power of 6 to convert this mu to Newton millimeter, and the cell name is mu_b_d_2. Next, I am selecting the formula for PT limit. PT limit is the maximum percentage of steel for the singly reinforced section, and we are watching the formula for PT limit, which equals 100 multiplied by 0.36 multiplied by FCK, multiplied by XU_max_D, divided by 0.87 multiplied by Fy. Here, FCK is our grade of concrete. XU_max_D is the value of XU max by D. Fy is the grade of concrete. By copying this formula from the formula box, I am pasting it into cell F13. As a result of this, we are watching the value of PT limit equals to 1.194%. The name of the cell F13 is PT_lim. Next, I am selecting the formula for percentage of steel required, and the formula is equal to round 100 multiplied by mu_b_d_2, divided by 0.87 multiplied by phi multiplied by 1 minus 0.416 multiplied by SU_D, up to 3 digits. By copying this formula, I am pasting it into cell H13, and we are watching the value of PT required equals 0.379%. The name of the cell, F13, is PT_REQ. Now, for the safe design, we have to check the following. 1. The value of XU must be less than or equal to XU_max by D. 2. the value of mu_b_d_2 must be less than or equal to mu_lim_b_d_2. 3. The value of pt_prov must be greater than or equal to pt_min. 4. The value of pt_prov must be less than or equal to pt_lim. In the next portion of this video, we are going to watch that. Now, it is time to check the safety of our design. You are viewing 3 boxes below the output data. First, fill the cells B14 to H14 with a green color. Then, select the formula for check number 1 from the drop-down menu and, by copying the formula, paste it into the merged cells B14 and C14. The formula is equal to if xu_d greater than xu_max_d, then check depth, otherwise OK. Check number 2. From the drop-down menu, select the formula for check number 2. Copy the formula and paste it into the merged cells D14 and E14. The formula is equal to if mu_lim_b_d_2 greater than mu_b_d_2, then OK, otherwise check. Check number 3. From the drop-down menu, select the formula for check number 3. Copy the formula and paste it into the merged cells F14 and H14. The formula is equal to if pt_req greater than pt_lim or pt_prov less than pt_req or pt_prov less than pt_min, then check reinforcement, otherwise OK. Our checks are ready. Now select the cells B14 to H14 and go to the Home tab on the ribbon. Select Conditional Formatting, select New Rule, select Format Only Cells that contain, select Specific Text, select Not Containing, type OK. Our checks are ready, and we are viewing that all the checks for the beam are OK. Now, it's time for testing. To test this application, first, I am changing the depth from 450 mm to 350 mm. Look, xu_max_d is less than xu_d, and it is recommending to increase the depth of the beam. Now I am changing the depth from 350 mm to 400 mm. Once again, our design is OK. Now I am changing the diameter of the bar from 20 mm to 12 mm. We are viewing the recommendation to increase the percentage of steel. Now I am adding 2 numbers of 12 mm bars as a second layer. Once again, our design is OK. In this way, we can test our program by increasing mu and other parameters, such as FCK, FE, etc. This Excel application summarizes the key design criteria for singly reinforced sections under bending moment. We've covered 3 essential checks in this video. Design Criterion 01 ensures the neutral axis depth, XU, is within acceptable limits for ductile failure, by comparing XU by D with XU max by D. Design Criterion 02, verifies moment capacity, calculated factored bending stress, MU by BD square, must be less than or equal to the limiting factored bending stress, MU lim by BD square. Design Criterion 03, check steel reinforcement, provided steel percentage, PT, must be between minimum, PT min, and maximum, PT lim, allowable percentages for strength and ductility. These criteria ensure safe and effective design. That concludes part 2 of Excel for IS-456 beam design, bending, with SP16, part 02. Next week, I'll upload part 3, which will demonstrate how to control shear stress in a beam. I hope you found this tutorial insightful. Your feedback and questions are welcome in the comments. Thank you for watching, and I look forward to sharing more Excel tips with you in the next video. If you found this video helpful, please like, share, and subscribe.